Cool, awesome. So in last week's meeting, we talked about VLLM and especially the initial paper by VLLM folks on like page attention and how that was a new how they applied the rules, the principles of page memory, which we use on like operating systems and traditional CPU-based systems to like the GPU memory, and how they're able to use like the memory more efficiently, considering like the KV cache is dynamic and is huge per request. Today's focus is going to be more on like distributed serving, especially disaggregated serving. Both prefill and decode have different needs, like the same stuff we saw last week. Prefill is compute heavy, decode is memory heavy, and it's also iteration based, so it doesn't really doesn't saturate the compute. So these require different optimizations, and like how would you set up like a full distributed serving system based on these optimizations and efficiently use it. There was, no, that not there was, there is a paper by, I believe this is the UCSD. No, this is, yeah, and this was UCSD plus some people from other universities. Um, this was a paper on like disaggregated prefill and decoding for good put optimized large language model serving. Um, they have also written a blog on it, which is super awesome because it gives us like more summarized view of what they're trying to do here. But before I dig into this, I wanted, sorry, Raja, go ahead. Yeah, I can't hear you. You're muted.
I'm sorry. Good put. That's not a term I'm familiar with. Do you know what that is?
Yeah, we'll go to that.
Oh, okay,
But
great. Great.
yeah, we'll go to that. But yeah, before we go through like what is LLM serving and why do we need like a distributed serving system and why we can't do it like a single node serving, I wanted to go through first the basic concepts of like if you were to optimize from scratch the serving for LLMs, how would you go thinking about it? So we'll just cover some of those concepts first, and then we'll come back to this blog and go through it. Everyone can see my screen. I'm on the bento. I'm a static
Yes.
kind of. Yeah. Okay. Awesome. Um, so unlike training, where you already have like your entire training data set ahead of you, already available to you, so you can create whatever batch sizes you want, and you can truly optimize for larger batch sizes. Serving is a bit different, and especially if you're doing real-time serving and not batch inference. So sometimes when you do like offline eval or stuff like that, you can still saturate your compute because you can create as big batch as you want. But if you're doing real-time, like conversing with chat gpt for example, then it is you are optimizing for time to first token and time to next token and latency, so you really can't create batches statically, basically just say like, hey, after I have 1000 requests, I'm going to go forward and schedule my forward pass on the gpu for example. So static batching is basically you say your static batch size is n, you wait for those fixed number of requests, so n requests to be collected, and then you do the forward pass on the GPU. This is really useful for offline workloads, but not useful for real-time workloads. So that is one thing. The second, in case of the LLM world, when you do static batching, you realize your time to first token is very high because if you're waiting, like for example, in this example, R1 came in first, and now we are waiting for R4 to come in. So your time to first token is going to be pretty high. But once it is scheduled, it is guaranteed to be finished, and only then the next batch will be scheduled. So your time to next token is going to be super fast. You're not waiting to be scheduled again for like every token you're generating in the decode phase. So this is kind of yeah, so this is the kind of static batching thing. It doesn't really work well um, for real time. Also, it doesn't work well because all requests are not created equal. Sorry, Roger, go ahead. Yeah.
Oh, I was just wondering, the light green batch that we're talking about here, is that representing a single token generation, like one pass?
No, it represents a request.
Okay, and which may run for some number of
Yeah,
tokens.
which may
Okay,
run for some time. Yeah,
okay,
yeah,
great.
yeah.
Thanks.
Yeah, so this that is the second disadvantage of this is like you some requests might be very small and might generate very small responses, but others could be like lengthy and step like go through like generate 5,000 tokens or something like that. So in that scenario, like yeah, if your R1 is short but your R2 is super long, R1 has to wait for R2 to finish before like not R1 has to wait for R2. Sorry, that's incorrect. R1 will already finish it, but you will pad R1 as long as you are doing stuff on R2. So you'll be wasting compute, basically, because R2 is running very long. Um, so to solve the first problem I talked about, like batching for real time doesn't really work very well. Um, there's this concept called dynamic batching. It's very well supported in conventional inference systems like TensorFlow serving, Triton inference server. They all support it. The basic concept is you don't have a fixed batch size. You have like a variable batch size, and you say I can wait for a certain time window. I will wait for the request to come in. If they do not come in, then whatever I have, I will schedule. So, for example, in the first one, it didn't wait for R4 to come in. So you can say like, hey, the max batch size I can have is 4, and then my timeout window is like 3 milliseconds. And if R4 comes after those 3 milliseconds, I'm just going to schedule R1, R2, and R3 and go ahead. And then in the second batch, oh, I was able to fill in all the 4 spots. That's great. And in the last batch, you can see they weren't able to fill 4 spots. You could just fill in 2, and that was okay. So this is like you can think of it like that the timeout parameter is like a parameter you tune to trade off between latency and GPU efficiency in some way. So that's basically what this represents, but it has the same problem for LLM serving as we discussed before for this, where if R2 is very long, you're wasting compute for other short requests which have already finished. No other request can take its place. Um, that's where this comes in, which is continuous batching. It's called different things at different places. So some places I read it's called iteration level scheduling, some call it continuous batching, some call it token level batching. But the idea is simple. It's also, yeah, they also call it in-flight batching. But the idea is similar. So if you look at this diagram on the left hand, the table on the left hand side, this is your batch, which contains 4 requests. Um, and these 4 requests, they will continue and they will end at like different point in time. So the yellow is the prefill phase, and then the blue is the decode phase, and then the decode will end at this particular point in time. So from the right table, you can see like the request 1 started, it finished at timestamp 5, request 2 finished at timestamp 7, and then so on and so forth. Now, in this scenario, if you were doing static batching or dynamic batching, these even after request 1 has ended, you couldn't really use these 2 slots for timestamp 7 and 8 because you are like, oh, I have a fixed batch. I don't change the batch once it starts running. And then your longest sequence becomes the bottleneck. So you're kind of wasting compute on these. So the idea of continuous batching is like you take in the next request and you schedule it in that empty spot, like after certain time intervals, you detect which requests have already finished and then you add a new request. So in that way, you don't have wasted compute. Another thing is they make like, which was also true for static and dynamic batching, but I just want to highlight it because I didn't realize it before, was you mix up the prefill and decode requests in a single batch. So you in most of the batching techniques I read online, the prefill and decode are mixed in a single batch. So here, for example, this one is going through prefill, but then this one is going through decode kind of phase. And that has its own challenges. Yeah. But yeah, but overall, these are the different batches. Static and dynamic have been there for a long time. With tokens, you have two levels of hierarchy. One is like a request and then a token. So you introduce like a token level batching system. And that is what being used until this is what being used in like VLLM and stuff like that if you don't use like disaggregated inference. Yeah. Does that make sense? Okay. So coming to the disaggregated inference. So first, um, these guys introduced the concept of throughput versus goodput. Like throughput is basically the number of requests you can process per second. Um, wait, where do they define goodput? Yeah, so they introduced goodput, which is the number of completed requests per second that are there to the SLOs like TTFT and time to first token and time per output token. So the idea, I think the argument they basically made is when you just optimize for throughput, you're not optimizing for latency because you will have better throughput if you wait long enough to collect enough batches and like organize your batch intelligently and stuff like that, you can always increase your throughput. But that's not necessarily going to improve the user experience or like they call service level objectives on like, hey, I entered a prompt in a chat thread and now I'm waiting for a long time for the first token to come in, then 10 tokens come in, and then for the next token after that, I'm again waiting like certain amount of time. It is not a good experience. So they introduced this thing which is called as a goodput, which is the number of completed requests which satisfy the TTFT and TPOT requirements that you set up. Um, so so yeah, this is a good example of how do they define goodput. Assuming an application requires time to first token of 200 milliseconds and time per token of 50 milliseconds for at least 90% of the requests. So then goodput is equal to maximum request rate you can support when this is happening. So here is a figure they have. Um, So what? Okay, wait, I forgot what the figure was about. Um, yeah, so this is the you have like the number in 1 second you have 10 requests completing. But then the time to first token for only three of them is good, and time to TPOT, time per output token, is only good for three of them. Then your good put is just three per three out of 10 instead of 10 requests per second. Yeah, Raja.
Yeah, and I was wondering for the two different use cases that they talked about. One was like a chat box response, I think, versus chat? So like if you're doing a research thing, you have certain service levels. If you're doing a chatbot type of thing, you have a different service
Right.
level. But I'm wondering, to me, it seems like there's another one which a lot of them seem to fall down at, and that is if it's like a voice interface to a chat to an LLM, it seems like it has even tighter, like the TTFT, I guess, is going to be
Mm-hmm.
very tight. You expect you don't want to wait. Have you ever had a conversation with
Mm-hmm.
speech input and sound voice output? Um, that the latency is much more important than the throughput, I think, for those.
Yeah, yeah. So it also depends on how you design your system. Like I don't know how different chat like different agents voice interface works right now, but initially when I read about it like 1.5 year or so back, they usually have a different model for the voice to text conversion sometimes, and then they
Hmm.
feed it in that text into the LLM, and the voice to text conversion model can be smaller so it doesn't um, it might have different constraints, but I agree with the concept. Like you would have different TDFT and different SLAs for a voice to text conversion than to like the text, than to like just going through the prefill and decode phases. But yeah, I'm not sure how multimodal models do it, but like for most of like the question answering chatbot types, I just think they have a different smaller model to convert the voice into text. Yeah.
Yeah, yeah, yeah. It seems like there's something related to you don't you want it to start responding right after you stop talking.
Yeah. Yeah.
Sometimes when you're interacting with these, it feels like it doesn't even submit the request until you stop talking, and then there's the delay for it to figure out what the response is, and then
Right.
it thinks it has the whole response figured out before it starts speaking to you.
Right.
Um, yeah. So
Yeah.
I don't know. It doesn't sound like that's what the good put, I guess, could be address that use case. It'd just be a different set of parameters.
Yes. Yeah. Yeah.
Okay.
Yeah. Yeah, so they basically summarize all the terms. Most of us already know all the terms, so I'll skip that. Um, yeah, so this is the part where they make a claim that having continuous batching necessarily doesn't help with the good put. It might help with the throughput, but it doesn't help with the good put. Um, Wait, let's just see what this video says in the end. Yeah, I think it's just explaining the pre-fill decoy thing. Yeah. Okay. So the the same they use the same argument that we saw for the paged attention as well, is basically the pre-fill decode phases are very different in nature when it comes to resource consumption. Prefill is compute bound. So even if you have a very small batch of prefill or a single big prefill, you can easily saturate the GPU computation. Decoding, it is not at all compute bound. Like you would need, because you're only generating or processing one token in one decode step. So you would need like a very high batch size to to hit your computation limit. But it is because of the KV cache and stuff, it can easily hit the memory bandwidth. So the resource requirements are different for both of them. So that's why, since they have two different natures, co-locating these two phases in a single GPU is not optimal. One is they interfere with each other. We'll see an example they have of how they interfere with each other. And the second one is when your resource requirements are different, you want to scale them up differently, you want to parallelize them differently. Like, for example, if you have a system which is heavy on prefill, like it's taking in large amounts of input, but like output is generating is just like small short sequences, then you would need like computation heavy stuff for the prefill, but you don't have that much memory requirement. So you could like just have a small GPU on the side which does decode or something like that. So the idea is like, and also you'd use different parallelism for prefill and decode. So given these two constraints, it's very hard to have like higher good put. So that's the reasoning they have for proposing this disaggregated inference. So collocating prefill and decode causes interference. So this is a good example in continuous batching. You batch request one and request two together in one GPU. And in one so prefill is like a one shot thing. So once you schedule like in in a single forward pass you're going to finish the prefill, but that forward pass is going to be huge. Decode is also one single forward pass per token, but that forward pass is going to be very small. So in one unit of execution, basically your prefill is going to be very big, and you will still have some time wasted because you're not able to decode something else until then in a single batch. And if you hit multiple such prefills together, then you're going to have more latency. So you're going to start seeing latency for time to next token. Ted?
Hi, Neha. Yeah, I think ultimately the point still valid, but it would be not as bad if you do chunked prefill instead of one giant prefill, right?
Yes, if you do chunk prefill, it will be better. Yes, for sure. Yeah.
Thank
But
you.
I think it depends on so I don't have numbers. Yeah, this is the same question I had where people do chunk prefill, so there's a layer on top which divides your prefill into um, smaller token lengths, and then your prefill is limited. So then you can control how much this time wasted is there. But when it won't basically come down to zero, but I'm not sure how significant it will be. Like even if, say, suppose you control your chunk prefill to a very small token length.
Yeah,
Because if,
thank you.
yeah, because it's like it gets aggregated over every request, like every, if it's getting aggregated over every token decode, like the accumulation might still be big. So this was the part I didn't find any resources like on like how much does it really matter? Yeah. Yeah. So this is one of the reasons. So you're still wasting some time. You have a higher time to next token, because you might have had some requests which are larger, which have high prefills. And also Ted, to your if we do chunk prefill, then we would increase the time to first token. So I think it's a trade-off between the two metrics.
Yeah, I haven't tried implementing it and seeing exactly what the performance is. In the best case, chunking doesn't really cost you very much on your
Okay.
prefill time.
Right, right,
In,
right,
in
right.
theory, but in practice, I don't know
Yeah,
how
yeah,
close you can get it.
yeah. Yeah, so this is the first argument, and the second one is the over-provisioning of resource to meet SLO. So you basically have this setup where you're optimizing for memory and compute together. So if any of them hits a bottleneck, even if memory hits a bottleneck, you need to add more memory and compute kind of together. So you end up over provisioning resources. And this was actually the parallelism one was interesting one. I hadn't thought of this before, so I was intrigued by it. Um, the parallelism strategies, whether you do tensor pipeline, are coupled for prefill and decoding computation. So if you're using tensor parallelism, you're using it for both prefill and decode because you're co-locating them. But the optimal strategy for the pre is usually different. So, like for example, when your TDFT is stringent, like you want an immediate response, and time to the next token is loose, the prefill phase prefers tensor parallelism, while the decoding phase prefers pipeline parallelism to boost the throughput. Basically, yeah. So this was also like you might want to choose how to parallelize differently for the two phases. Um,
Neha, Terry's got his hand up.
yeah, there you go ahead.
Yeah, yeah. Yeah, actually, about a previous topic, how does the chunk prefill help with this case?
So chunked prefill is basically a way of saying that I will make my you have every request is going to have different prefill, different token length for your prompt, right? So your prefill token length is going to be different for each request. So some might have very small and some might have very huge. So you can have like 100 token prompt and you can have like a 3,000 token prompt. Um, Chunked is a way of saying that I will divide my 3,000 token prompt into a fixed token, say suppose 100. And instead of doing the entire prefill in one go, I will do it in 30 parts basically. So the green part here becomes fixed length instead of variable length, and you tune that fixed length. So you control how much wasted compute is there out here. Um, the
So,
Go ahead.
so it's kind of like split this green bar into smaller chunks,
Yes,
and
yes, yeah.
then so you can do the decode, like the decode of R1 earlier than this picture. Is that how I should
Yes.
understand?
Yeah, so this green will become shorter. So if I divide this into half, basically, this will also become half, basically. So this will move towards the left. So your third one, two, three, fourth token here would happen faster, and your fifth
Okay.
token will happen faster. But at the same time, when you finish doing your green block, when you finish doing your prefill, you usually return your first token. But now, since you divided this into half, this will get pushed ahead. So your time to first token will increase. So this will be pushed.
Oh,
Yeah.
I see, I see. Okay,
Yeah.
yeah, yeah, I see. Thank you, thank you.
And there might be additional overhead with chunking, which I believe, which as Ted mentioned, might not be a
Mm,
lot, but we are not sure. Yeah.
Yeah, yeah, I think I understand. Thanks.
Yeah. So yeah. Um, yeah, so basically what they say is they separate out the prefill and decode into two separate GPUs. Instead of being on the same GPU. So when a request comes in, I'll wait for it to come in again. Yeah. So then the request comes in, it first goes to the prefill worker. You generate the KV cache, and then you transfer the KV cache to the decode worker, and the decode worker does the decoding, and you get the output. So now you can scale this independently and this independently, and you can have different parallelization strategies across the two. The one thing they talk about below, but one of the reasons this wasn't done before is like the challenges with the KV cache transfer. So we saw last last for the page attention, how big the KV caches can go, up to like gigabytes in size. So when you have them on separate GPUs, you're kind of transferring that many gigabytes across. And that is the argument they make below, that they are able to manage it and it's actually not that big an issue. So let's just go through what they have. But yeah, this is the only reason why people, I mean, this is how the traditional distributed systems also work. You usually have one system for each particular task if the resource requirements are different. But yeah, Raja.
Yeah, I'm a little confused. In this, when you divide it this way, does it mean that the prefill worker is always going to be compute bound and the decode worker is always going to be kind of memory bound,
Yeah,
memory constrained?
yeah.
And why is that a good thing? It seems like
You
a
can
bad.
you can use different hardware. You can use different scaling strategies, like so it's more about being cost efficient while trying to meet the TTFT constraints.
Okay, so this decomposition is better for good put, and then
Yes.
you design other aspects of the system to try to make it cost effective.
Yes. Yeah.
Okay, okay, I
This
get.
this this breaking up is also good for cost. Like if you choose different hardware for prefill and decode here based on, like, one is compute bound, so you can choose high compute. The other is memory bound, so you need to use high memory bandwidth GPUs. So you can also be cost effective that way. Like if they were on a single node, you would always need to choose the GPU which has the highest compute capacity and highest memory capacity. But now you can be like, it's okay for prefill, I don't need memory. I can choose a low memory
Got it.
instance. Yeah.
Okay.
Um, yeah, so so we serve a 13 billion LLM on a single A180. So this is the same one. This is the same model which we saw for the page attention last week, and the same hardware, with the synthetic workload inputs of length 512 and output length 64. Um, Following, how do you pronounce this? Poisson arrival. We gradually increase the request rate and measure how the two latencies change in figure 6. So this is the figure. Let's look at the time to first token. So if you've co-located, then as you increase the number of request rate, your time to first token also increases. Um, and we said for good put, it's like less than equal to 400 milliseconds, a TTFT. So essentially, it's like 3 requests per second. With disaggregated inference, they use two GPU for prefill and one GPU for decode. And then you can do a request rate of 5.6 with less than 400 millisecond. And then the same trend is for decode as well. Yeah, so you essentially have like 2x. Um, Yeah, this is per GPU, by the way, and this is like two. So they kind of do the math and divide it by three. So you kind of have like three times, use 2x the QPS per GPU based on that. Yeah. Yeah, so they just go through the graph here. So yeah, the good put is measured. Yeah, so this is the interesting. There is more. If we have bandwidth, we'll go through this. But there is more interesting stuff which comes in on where do you place your pre-fill workers and your decode workers. So ideally, if you can place them on the same host, then you can communicate on like the GPU to GPU network which is much faster compared to having them on like different hosts, and like how they're connected also matters. So they kind of go through different combinations of like how should you place your prefill and decode workers and how they should communicate. There's also this concept of stickiness. So you want the same prefill worker to talk to the same decode worker all the time. So you kind of I wasn't sure what's like if you're not caching anything, I didn't know what was the advantage. But like if you're caching on the decode side, if you have continued context which is coming in, then it's easier. You have to transfer less data, so that is also there. Yeah, but you just can't like if you just randomly put in prefill and decode workers, it's not going to be optimal. And I'm pretty sure for this also, they're probably on the same host or something like that, or like intelligently placed for it to be better. So the KV cache transfer, yeah, so this is where they talk about the KV cache transfer bottleneck. Um, at first glance, like KV cache is a big memory expenditure and LLM inference between GPUs sounds like a bottleneck. However, they show the opposite. With proper placement, KV cache transfer can effectively minimize to be as low as less than the time of a decoding step, uh, thanks to NVLink and the PCIe bandwidth. Um, so they assume I believe this is the latest PCIe bandwidth for the intranode network, so the in-host communication between GPUs. Given a request with 2048 token, they estimate the latency given a PCIe bandwidth. Oh no, this is not. Oh, this is not. This is intranode. Sorry, this is not in a single host. It's a cross host. Yeah, PCIe is a cross host. Yes. So yeah, they estimate this is the latency for transferring 2048 tokens associated KV cache across the two. And this they say is smaller than the decode step, like a big decode step. So for long sequences and for short sequences is low. So if you can it's kind of equivalent to saying like you're going to do one extra decode step. So if you're generating 10 tokens, your latency will be equal to generating 11 tokens, kind of. So that is what I got from this KV cache transfer. And then they evaluate the good put across the different this is VLLM at that time, so this is not VLLM right now, and this service there this is basically disaggregated prefill and decode system they've built. So this service their system VLLM is that time, not right now. And then they basically show that you have a higher good put for this. And yeah, this is where they talked about chunk prefill. So yeah. So Terry, to answer your question, the key idea for dynamic split fuse is to split a lengthy prefill into smaller chunks, thereby forming a batch that fully engages the GPU by combining. So you take one chunk and several decoding tasks, and that forms one batch. So you'll need multiple rounds of batches for doing one prefill if you're using chunk prefill. And the key is choosing the chunk size. So you want to keep your GPU fully utilized, but you also want to have enough space for like the other decode workers to work and not increase the latency there. Yeah, so for TT, yeah, so this was the stuff we were talking about. Like if you're doing chunk prefill, you have a higher time to first token. because you're going to go through X number of iterations versus just going through one iteration. Um, Setting the chunk size would double the TTFT for us. Yeah, so the same logic, you'd go through more and more. Okay, wait, let me go through this. Would double the TTFT for all, yes, extending beyond 5 and 2 because you're setting the chunk size to 256, so you can have max, and the prefill length is of 5 and 2, so you need more number of iterations to go through the prefill phase. Now, even if the chunk size is optimized to nearly maximize GPU usage, chunk prefill significantly increases memory access for prefill tasks. Oh, so this is, I believe, the hidden cost, Ted, which you were saying about. I think the cost is not in the chunking, but it's like you need to load the KV cache again from the GPUs for each subsequent chunk. So then it becomes longer. Translating loading operations compared to in the unchunked setup.
Okay, yeah, that makes sense. I
Yeah.
mean, if you only have one GPU, it probably makes sense to do chunked prefill instead of one giant prefill.
Right.
But they're saying, I don't remember which color was which. The prefill was it green, blue? But it's the long one, right?
Right.
And
Yes.
so
The prefill is the green
yeah,
one.
here,
Yeah.
the long green one. So they're saying if you shorten the green one by doing smaller chunk size, then the blues are happy. But then that
Right.
means you need to do extra numbers of green chunks
Right.
because they've been made so small, and that delays first token. If you make the green bigger, then that delays
The next
every other
token.
token, all the
Yeah.
decoding in between.
Yeah.
So if you're unless you're just super duper lucky that the GPU resource is perfectly matched between the green and the
Mm-hmm. Yeah.
and even then you have this overhead due to the
Memory
AV cache
access.
between
Yeah.
chunks.
Oh, yeah. That. Yeah.
Yeah, and by the way, I think the KV cache still the keys need to be loaded between what otherwise would be the chunks. But because you're doing it in one large operation, the the code is optimized in order to keep
Mm-hmm.
that in SRAM instead of going back and forth to high bandwidth memory.
Right. Yeah. Yeah.
Thank you.
Yeah, so this was the initial paper these guys had. They also had this just released like a few days back, which was when they released it, it was just a paper, but now there's an entire ecosystem around disaggregated inference. So there's like all the NVIDIA Dynamo LLMD, I think was released just this year. They all act as the orchestration layers for like routing the requests around and like communicating the prefill and decode workers. The core engine is VLLM, SGLang, and others. The KV cache, a recent trend with LMCache, and I believe Mooncake is by Kimi folks. But like the recent trend is also to make the KB cache disaggregated. So instead of like when we looked at page attention, the entire KB cache is on GPU, but now it's like, okay, you can go to CPU, you can also load it on a disk, you can also load it on a Redis cluster remotely, and then fetch it from there. And the different optimizations in network like RDMA and et cetera, which help you to fetch that KV cache faster. And I'm not sure about what the hardware improvements are recently. But if you guys are interested, we could just go through some of these new systems which have come up. Um, Otherwise, we could go through the paper and see other option is to go through the paper and see if there's anything interesting about like the placement of the workers. Yeah.
I think the broader exposure that these new ones would be, I
Okay.
would think.
Okay. Awesome.
Yeah, I'd agree.
Okay. Um. mm, yeah. Okay. So we basically start with the orchestration layer and then go down. So the first one was like NVIDIA Dynamo. This was just announced this year, I believe Jan or Feb at the GDC. Is Dynamo is one of the um, mm, yeah. So Dynamo introduces prefill and decode workers as first-class citizens and connects these workers using a KV-aware router. So the idea of a KV-aware router is basically when you route a request to a particular GPU, you try to route it to the place where you know the KV cache for this request or the context for this request is already present. So this is they connect these workers using a KV to aware router to efficiently route requests between like the prefill and decode instances. Um, Centralized. So in my view, this is more about just like routing and like instead of building, if you were to build like disaggregated inference from scratch and like define all these sticky routing, define the concept of prefill and decode, you kind of get a template here and you could simply just deploy it with your model and your inference engine of choice, whether it's VLLM or like SGLang or TensorRT LLM, and you get an out-of-the-box implementation which handles some of these stuff by independently. They also handle some of the networking stuff independently. They introduced called NVIDIA Nixel, which is a point. It is not. I was confused a bit. I thought it was a different kind of communication protocol or a communication how do I describe it? A different kind of protocol to talk between two hosts or two nodes. But this is actually a library which provides an abstraction over all these different types of networks you can have, like via NVLink, via InfiniBand, PCIe, etc. So like CPU to GPU, GPU to GPU, CPU to CPU, etc. They just provide an abstract layer. So you can think of it like your KV cache could be located anywhere, but you don't really need to know whether it's on CPU or GPU. You just like say, hey, get my KV cache from this point, and it will use the appropriate network over it. And they definitely demonstrated performance on like NVIDIA GB200. And yeah. This is the I hadn't heard about this until I read this, but they basically have a new hardware to embrace, which is built like with this aggregation in mind to serve like long context inference windows, inference workload. Um, so yeah, that was about NVIDIA Dynamo. The second one was LLMD. This also just came out this year. This I felt was more like Kubernetes related stuff, where you're like, you can take care of deployment, you can take care of auto scaling, you can take care of auto scaling independently for your prefill and decode. You could have heterogeneous GPU clusters. So you're instead of just having like a huge cluster of like NVIDIA GPU, you could have a mixture of AMD and NVIDIA and still be able to schedule your workers. So it felt more like the Kubernetes world, which is where it's taking care of the operational load on top. Ray also supports disaggregated inference in Ray serve. I I tried to look for resources if this is actually used for online serving, but I got a feeling that this is used more for offline batch inference. Um, the Dynamo is like a more popular choice for online inference compared to Ray. But yeah, they also support disaggregated inference and in their infrastructure. Um, this is like the orchestration layer. The Ray is like an orchestrator. Next, it comes to storage layer, the LMCache. This is this also currently moved under like the PyTorch Foundation stuff. But this is more focused on making the storage layer scale independently of like the GPUs. So they have this tech report where they talk about how you can have your how you can have your cache on GPU as well as CPU, and they also borrow some of the previous work where you compress the cache and write it to the disk in such a way that when you want to read it back and decode it, like they claim the performance is better. It's not that bad like as compared to like compressing it in other forms. So this work is actually built on two or three papers before that, one explored the compression techniques, the other explored the transfer, the different communication mediums and transfer. And then there's also a third type of papers which focus on like sharing the KV cache across requests. The request sharing which we saw last week was more focused on the prefill sharing. So if your request starts with the same prompt, then you share KV cache across it. But I believe there is, I don't know whether this paper talks about it, but I read it somewhere that LMCache also explores KV cache sharing, not just at the prefill level, but like in the middle somewhere. If your tokens match, then um, they have some way of working with like the cross attention in the model to make it work. But that part I didn't understand clearly. But this just acts as a storage layer, and it has different types of like this KV connector, which basically you can access the same KV cache from different hardware types. Mm, Mooncake, this was the first time I heard about it, not heard before. But this is also like a centralized KV cache abstraction, so that can hand off to any decode anywhere in the cluster. And then the core engine we saw VLLM, SGLang is similar. And DeepSeek is like very early adapter of this prefill decode disaggregation in their stack. Um, the team uses three prefill nodes and nine decode nodes, each with eight H100 GPUs to allow the system fully saturate compute during prefill while keeping decode latency tightly bounded. Um, yeah, each phase uses different dispatch logic for export parallel. The prefill phase runs with smaller export parallel and data parallel degrees to process large prompts efficiently, employs a much wider export parallel and high data parallel configurations to maximize group gen utilization and throughput. Can someone remind me what is expert parallel? Is it like you have different experts on different GPU nodes? So when they say they run with smaller expert parallel and data parallel degrees, so you have more experts on a single no GPU, so you have less number of GPUs, so less parallelization.
Yeah, that's the mixture of expert MLPs.
Okay.
So it's just how many experts you have per GPU. or how
Got
many GPUs you use to spread out your experts.
Okay, so for prefill, they spread out the experts less, but for decode, they spread out the experts more. That doesn't seem right. Oh no, it runs with smaller degrees. So I think degrees, they mean they have less experts on a single GPU. So it's reverse actually.
Degree usually means the total um, increase factor. So right, so data parallel 2 means that you've split your batches across twice as many GPUs.
Right.
Right.
Okay.
So smaller parallelism means fewer GPUs means more experts per GPU.
But isn't the prefill phase compute heavy? So if you want to lower TTFT, then you need more GPUs.
But does it mean you also, the prefilled isn't memory, doesn't have the same memory pressure, so you don't have to be as efficient about it. You can have more experts in the node that
Yeah, that makes
aren't
sense.
being run every time.
That
So that,
makes sense.
yeah, the weights are there, they're just not being processed each time.
Got it. Yeah, but then for
So I think
decode, go ahead, Dan. Yeah.
I think the way to think about it isn't that prefill is smaller. I think prefill you do based on your computing power. The way to think about it is decode is higher degree of parallelism, right? You don't make the prefill smaller, it's just smaller relative to decode. So what they're really saying is not this is how we do prefill. Prefill you just do based on how much a GPU can possibly compute experts. Um, but for decode, I think what you said, Roger, right, was you need more bandwidth, and so you end up spreading them thinner. And hypothetically, if you're DeepSeek, you may have some GPUs that are lower compute horsepower.
Mm.
Okay. Okay, yeah, that makes sense. Yeah, so this is just how they would normally serve prefill. They've not optimized prefill. They've optimized the decode to be different from prefill.
That'd be my guess.
Yeah. Okay, for KV cache transfer, they built the 3FS library to combine the throughput of thousands of SSDs and network bandwidth of hundreds of storage nodes to enable applications to access storage resource in a locality oblivious manner. Amazingly, the DeepSeek team open sourced these awesome frameworks to the community. Yeah. What is the future? Um,
Can I ask you a quick question about the storage? I'm just kind of wondering, how is that used? So is that, are we pushing like KV cache out to this to actual physical storage like an SSD?
yeah. Yeah, so you have your KV cache distributed across like GPU, CPU, and SSD. Um, and in the recent, I think they also support Redis in some way. And then you have different transfer channels, and you have a single interface like this KV connector. So the model basically just says, hey, get me the KV cache, and then it knows based on this manager where to fetch it from.
Interesting. So if I've generated, I've got a long context, I've been going back and forth for a bit in a single session, but then I stop submitting requests to that service. It would actually push that KV cache out potentially to SSD. And then
Yeah,
next time my next request, it'll have to load all that back in to continue on.
right. Yeah,
Interesting.
yeah.
And so it
Yeah, I
sounds
think
like maybe they had super ridiculously high level of striping on the SSD in order to lower the latency.
Hmm, makes
yeah.
sense.
So yeah. Eh, yeah, so the future,
You-
oh, go ahead.
Oh, sorry. So Ted, that ends up being a very customized hardware then for that application, I guess. So you're saying highly parallelized SSD access. Is
Yeah,
that
and my
right?
guess is you are sacrificing some throughput so that you can just have this burst of highly parallel striped, uh, you know,
Yeah,
data.
interesting. So you've got, what were the numbers? You said ridiculously striped. Like what type of numbers?
I don't know. It was the sentence that Neha was reading to say it was something, they said something about very high thousands of SSDs. So I'm
And then,
thinking you could theoretically stripe them all so that it's
Oh,
thousands way striping. So you're saying my
yeah,
stripe is 2000 wide,
yeah, that makes sense.
right? And so if you need 200 megabytes, then you're only reading 1 megabyte. Wait,
Yeah,
100 kilobytes from each of 2000 SSD or something like that, right? A relatively
yeah.
small.
maybe a really dumb question. What is striping?
So if you know tensor parallel, it's the hard disk equivalent of tensor parallel. So you just,
Oh, okay.
you say, my file, it has a, let's say it has a block size of 16K. If you stripe it 16 ways, then you store 1K on each drive. And then maybe you have some redundancy depending on
Got
your
it.
fault
So
tolerance.
it's
But
like parallel reading from key places together.
yeah, and so normally you wouldn't see, I don't think, striping higher than what, like 24 or
Okay.
somewhere around there? 30,
It's
40? I don't know.
and it's
Per
parallel
disk, yeah,
reading
it'd be
and writing.
quite a bit lower.
Yeah. It's parallelism on read and write. So
Hmm.
Right.
Yeah, and if you have write behind, then you can really speed up writes.
yeah. Yeah.
Got it. Yeah, so the future work, I think the big one is heterogeneous hardware, where you want to use a mix of all these different new hardware coming up across AMD and other companies. Yeah, there's like optimizing, scheduling, yeah, there's an entire area of like KV cache transfer. Like at the PyTorch conference, almost every other talk was about KV cache transfer. And a lot of them is by like NVIDIA on like how they're coming up with new ways of networking to like improve the speed of this KV cache transfer. Yeah, so this is heterogeneous hardware. This one was the interesting one. Yeah, beyond prefill decode disaggregation, a quieter but equally intriguing frontier is attention FFN disaggregation. Um, if you now believe in prefill decode disaggregation, then attention FFN degrad is a natural step to unlock even more speed up at scale. The rationale is simple. For a production size model, at decoding state, attention is generally considered as memory bound and requires more memory to store KV cache, whereas FFN is easily compute bound and can take up a large but constant memory to store the model weight. Separating both into tailored hardware devices can ideally make both rate reach high MFU with tight SLO attainment. Okay. So you use the same logic of memory and compute bound and then divide the decode even further between attention and the feed forward network.
Yeah, for training, you pay some level of overhead penalty when you break things up for more parallelism. But I think
Mm-hmm.
in decoding, it's much simpler because you don't have to store the gradients. You don't have to store the
Yes.
activations. Um, so if you believe that a 36 layer model, you could do pipeline parallelism on 36 GPUs easily by storing each layer on a different GPU, well, then why not 72 and just have every attention on its own GPU and every
Right.
MLP on its own GPU?
Right. Yeah, that makes sense. Yeah, so this was it for today.
Cool.
It's very cool.
This was
There's
a
a
cool
lot to
presentation.
wrap your head around there. All the interactions and hardware constraints and everything.
Yeah, it's telling me I should be investing more of my portfolio in some of these hardware companies too. Because these look like awful expensive solutions to the problem.
One thing I was interested in, Neha, you had at the top of that section it talked about like the different players that had products for disaggregation, and I was just when that flashed up, I didn't understand kind of how that all fits. So is this something where the concept of disaggregation was introduced, and now those players all have adapted to that?
Yeah, so this was, yeah, so they are kind of like just showcasing how much impact their paper has had in a way that like all these newer orchestration engines and core engines and like there's an entire new world of like KV cache management which is coming up, which is
Okay,
following the disaggregated path. So they're kind of
so it's
showing like, 18 months later, this one paper is now becoming the lingua franca of like serving. Yeah.
gotcha. Okay, so it's not like that there's distserve is not some sort of product that they're pushing out to all those core engines. It's just that concept has been implemented now by all of
Yeah.
those engines. Is that what it
Yeah.
is?
Yeah.
Okay, all right. Huh. That's interesting. Hadn't really even heard of this before. Had no idea it had that wide of an impact. Okay, any other questions, anybody? Clarifications? All right.
No.
Well, Neha, thank you very much for taking us down that
Yeah,
journey. That was a lot to bite off and chew on that, but enjoyed it very much.
yeah.
Yeah, if you can repost the links you had
Yeah.
posted at the very beginning.
Should I post it in the group, the Slack channel?
Slack
Yeah.
is better, yeah, because it
Yeah, that'll
persists
work.
Okay.
Yeah.
automatically.
Yeah.
Yeah.
And everybody can find it.
Yeah.
I'm